Welcome back, everyone. Welcome to the final part of day one, where we have a wonderful speaker joined us from different parts of the world. We have Dr. Shyam Digge, President and CEO for Equasource Technologies, joining us from US. And we have Dr. Hans-Georg Konrad, CEO of Promicon, joining us from Germany. Request Dr. Konrad to please start the session. And before that, before we invite them on the stage, we are really thankful to our associate sponsors, Equasource Technology Corporation, Promicon, and SITS in India, for supporting us for the second edition of CEMWHR Virtual Conference. Over to you, Dr. Konrad. Please feel free to share your screen.
Thank you very much. Let me first do that. Okay. All right. Hello, everyone, and thanks for giving me the time to talk to you on this last session today. I am the founder and president of Promicon, a company in Germany. We are located not far away from the German capital, Berlin, a little bit to the west of it. And our company has been around for over 26 years now, specializing in the flow of in the measurement of gas flows, process gas flows in the industry. Can everybody hear me well? Sorry, I see hear some mumbling in the background. And can you hear me well? It's fine. I guess. Okay, so let's start our session today. Actually, what I would like to focus on today is process gas flow measurement. We also call this airflow measurement because very often process gas is also air, but very often it's also combustion gas that we have to measure at various temperatures and also with different dust and dirt content. And that's a very difficult task, but it's very important and crucial, especially in the cement industry. I'm going to talk about our measurement principle, which is quite unique. There's nothing else on the market really similar. On the installation and the technical data. And of course, I'm going to talk about the advantages and the optimization potential in your cement plant. Cement plants are consuming huge amounts of energy, not only for the pyro process, but especially for moving process gas around the plant. So I'm going to talk about various options here. As I mentioned, we've been founded in 1995. We're located close to the city of Magdeburg in Germany, and we are actually going or selling our systems into the market of power, coal-fired power stations, biomass-fired power stations, into the market of cement, waste to energy, as well as all the smelter industries with a big focus on steel making. Our measurement systems are used for optimizing the thermal process. And if you had read our logo, Promicon, it says we focus on your process. We really mean that. Our company has been devoted to the fact that we not only sell measurement systems to the client, but we look into the installation. We even do CFD analysis of the big ducts to see where the measurement has to be located, ideally. We also understand a lot of process parts, so we can also give you the advantage or calculate the benefits and savings. So we are really a partner in your process optimization. And what we're talking about, of course, is energy conservation, ecological compliance, and at the end of the day, saving money, saving fuel, and saving electricity. So I'll just move on. Here you can see basically our system. Our measurement system is different from the traditional way of measurement. The traditional way of measurement is usually measuring the delta pressure over a certain flow resistance. So you have a venturi or you have an airfoil and you measure the delta pressure. When you have a lot of dust, this is very, very difficult because your pressure tabs keep on clogging. You can see in the low-hand right picture, we have pulled out a sensor out of a downcomer duct, and you can see how much dust is lying on the surface of that sensor. This dust prevents you from taking accurate readings with delta pressure measurements, and also with others such as thermal dispersion, hot wire anemometers, and also ultrasonic measurements have huge problems in this environment. Our measurement technology is unique. We use two sensors and we use a cross-correlation technique to measure the flow velocity in your duct. And here is how we do it. We have two sensors which are mounted along the duct. So basically, we're having one measurement upstream and one slightly downstream. And when I say slightly downstream, I mean about 300 to 400 millimeters of straight run. So very close together, you have these two sensors. And what these two sensors are sensing is basically electrostatic charge. All the particles going through the duct are electrostatically charged, so they will carry a positive or a negative charge with them. So as these clouds of particles move through the duct, they will leave an opposite charge on the sensor. And that means as the clouds come and go, we will see a current. We will see an electrical current on the sensor. How does that look like? Take a look. These are the particles going through the duct in your cement plant. Raw meal, cement meal, clinker dust. And this is what we measure. Our system measures these raw signals. And these are basically a time signature or a fingerprint of the clouds passing by the sensor, right? Now, as you can see with your bare eyes, the time signature on the two sensors is very similar. You can see this. The bottom and the top are very similar. But if you put them on top of each other, you will see they are similar, but they are time shifted, of course, because one sensor is upstream, one is downstream. So the big question is, how big is that time shift? And here comes the digital part of our measurement. We have these signals that we record, and then we put them into a digital algorithm, a so-called cross-correlation function. And this cross-correlation function will shift the two signatures until the point that they have the best match, right? So we have a calculation of time shift, and the cross-correlation function will tell us, okay, the maximum of the function is at, in this case, 52.1 milliseconds. So what our two sensors are doing is they're giving you a time shift. How long does it take the gas to get from one sensor to the other? And now we have the distance of the sensor, for example, 350 millimeters. We divide by the time shift and we get a velocity. So we can measure raw gas, process gas velocity. Taking the cross-sectional area of the duct, we can then multiply with this area and arrive at volumetric actual flow, right? Now, if you take the gas temperature and the barometric pressure, you can then also calculate the standardized gas flow on that location. That's all. It's a very simple way to measure. So you can put our sensors into any duct. You should have a certain minimum straight run upstream and a little bit of downstream if you are using one sensor pair. I know that in modern cement plants, some ducts are shorter, are more difficult. In this case, sometimes you have to use multiple pairs of sensors in order to get an accurate flow reading. Our company will support you with that. We will support you in finding the right location. We can give you some calculations and also experience on where to put our sensors in order to get a valid and accurate reading. Now, I want to let you know a couple of very fundamental advantages of this measurement. As you can see here, you only have a box and two sensors, and what you get is a 4 to 20 milliamp signal or a system fault signal for our measurement. And since our measurement is purely digital, and since we are only measuring time, time is the only variable that we measure, you will not have to recalibrate any drift or any zero span or anything. Our system is calibration free. It is recalibration free over the life of the box. And this is why so many cement plants around the world are using our system. We are installing these systems with all the big cement makers: Lafarge Holcim, Cemex, Italcementi, Heidelberg, you name them. Everybody is using these in modern plants, whether they're erected in India or in China or in Africa. A lot of new plants in Africa. Our system is usually specified in many, many plants from the start because it is a drift-free, maintenance-free, and calibration-free, recalibration-free system. Yeah. We also have a version that uses a so-called range extender if there is no dust available, but I think no dust is in the cement plant is rather a, it's not very common. We always have enough dust in the cement plant. So the setup I've shown you before is probably the one that you're going to use. So what is the typical, what are the characteristics of this system? First of all, we can measure up to 1,000 degrees Celsius of temperature. So you don't have to worry where we measure. We even have some special sensors ranging above 1,000 degrees Celsius. So even tertiary air measurement is not a problem. Measurement in the downcomer, measurement on the bypass, all possible. The velocity range, as you can see, we are measuring delta time. So we have a linear measurement. And that's a big advantage, again, over the delta pressure, because delta pressure has a square root measurement. So because of the Bernoulli equation, you have a non-linear measurement. The Promicon measurement is linear, and that shows in a huge turn-down ratio. The normal measurement that we have ranges from a few meters per second up to 100 meters per second. We could even go higher, but that's usually not demanded. So large velocity range. Dust concentration range. Many people ask me whether this is a typo. It's not a typo. It goes from 0 milligrams, from absolutely zero, to about 3,000 grams per cubic meter. So you can measure actually the raw gas out of the raw mill directly. Huge advantage in controlling the raw mill. Typical accuracy plus minus 2%. I say typical because this also depends on installation location, stratification, and other factors. So we will help you in order to establish what the expected accuracy will be. Repeatability, it says 99.95%. I think this is still not, I think our repeatability is even higher, because the repeatability is only depending on the accuracy of our internal digital clock that samples, right? So our repeatability is our biggest, the biggest advantage. Reaction time, smaller than 1 second. And again, you get 420 milliamps and IP66 NEMA 4 protection. So what are the main advantages? No K factors for calibration, no drift, no duct modification, no regular cleaning. These are the main advantages. I would like to name another one that has not been on this presentation explicitly, but it's worth mentioning. We have 2 sensors. We are measuring a time shift, and we are calculating the velocity by the distance between the 2 sensors. Why is this important? The distance between the 2 sensors is a vector. It's basically the distance that's orthogonal or perpendicular on the 2 sensors. Why is this so important? It is very important because we are not measuring any lateral velocities or any swirl component. If you have a swirled flow, our 2 sensors will tell you the velocity vector that is in line with the pipe axis. And swirl is one of the most common factors for mismeasurements on these large plants. If you have an airflow and it goes around 2 corners, up and right and down, then you will automatically have a swirl, right? So swirl will not affect our measurement at all. And therefore, it is very worthwhile mentioning. So I would like to use the rest of the time that I have to show you some typical examples of where we measure and what we do in a cement plant. You can see a typical cement plant here. You can see a vertical roller mill, raw mill, and the outlet of the raw mill you can see, and also you can see the recirculation duct going back into the raw mill, right? So raw mill is a very big focus on our measurement in cement plant. Then, of course, further right, you can see the bypass, also a very important measurement. And then on the kiln preheater tower, you can see the downcomer. The downcomer is basically this is our most popular measurement. We sell more downcomer measurements than anything else because it tells you something about the main gas flow through the whole pyro string, which is a very essential value, not only for operating the ID fan at a lowest possible energy consumption, but also having the right flow and the lowest possible process noise in your pyro process in the rotary kiln. Then further to the right, you can see the TA, tertiary air measurement, especially for people in India, I think at these times quite interesting, because the tertiary air is the oxygen input to your pre-calciner. And the pre-calciner is a big source of thermal NOx, and NOx emissions in cement plants are a very big issue in India at this moment. So better control of your tertiary air into your calciner is a big point. Now, you can either create the NOx in your pre-calciner, or you can create the NOx in your main burner on the kiln head. So to mitigate these both, you need the correct airflows, and the TA measurement is a keystone for that. Then, of course, also part of this conference, waste heat recovery control. Waste heat recovery is also very big interest in our measurement, and I will give you some examples of that as well. How much enthalpy are you getting into your waste heat recovery boilers or your other parts that you want to reuse the heat? What I'm going to talk about, of course, is not only be saving waste heat, but also saving electricity. I mentioned it before, 40% of your energy consumption with all this really is electricity, and most of it is used to run your fans correctly. So fan operation is a huge electric load factor of your plant. Let's start with the raw mill. The raw mill is one of the most important systems in the plant, and it has a huge energy consumption. Again, here, a big part of the energy consumption is really related to ID fan consumption. Now, how is the ID fan operated? You all know how your operators struggle to keep the raw mill operated correctly. So the ID fan has to be operated in a way to achieve a certain minimum flow. Yeah, if you underdraft the mill, you will fill up the mill will drown, and the mill will trip eventually even, which is a major event. Nobody wants that. Raw mills are big monsters. Nobody wants to shovel out a raw mill. Cleaning out a mill is a big thing. And we found that in many places around the world, operators tend to overdraft the mill in order to have a safety margin on the air draft through the mill. So the security factor is there. Usually it's like 15%, sometimes even higher, right? Now the big point here is the Promicon system allows you to have an exact measurement of the raw gas through the mill. And by that, you can reduce the safety margin to a much lower value. And this results directly in a huge saving of electrical energy on the mill fan, because the mill fan is usually a very big fan for these sort of mills. This is an example. Please don't take these numbers for exactly right to the last digit, but they are just showing you how much the order of magnitude of savings is that you can expect. Yeah, this is what we have achieved, for example, on Holcim mills in the US. these are the savings, continued savings of 150 kilowatt hours for 150 tons per hour mill. No, this is wrong, 150 kilowatts, sorry. So by considering the electricity costs, this is about 10 euros per hour, right? So after 1,500 hours, you can have an ROI. It's already achieved. You will have a huge payback and a low payback time. ID fan, Kiln ID fan regulation, downcomer. This is another big thing. You have another big ID fan using a lot of power on the downcomer. By the way, I think most of the fans of this world are not adjusted properly. Most of the fans use too much energy, and in most cases, the operators are not really running on the fan curve. Most of the time, fans are operated outside the fan curve, and therefore you use too much energy. But on the downcomer, again, it's very important to note: are you overdrafting, especially on the short term? You regulate the amount of draft through the kiln, usually by measuring the oxygen. And measuring the oxygen is fairly complex and fairly difficult because the values are jumping around and you don't have very regular readings. So very often the ID fan is not operated in a flat line, and therefore you have, on the high end, you're using too much overdraft. And the big issue here, of course, is that the fan curve is non-linear. If you have a big ID fan even with a frequency inverter, then the energy consumption rises to the third power with flow. So if you reduce flow by 10%, you can reduce power by 27%. So reducing fan power consumption is a very, very valuable thing. The way people do that, or the solution to this problem, is usually the fluctuations are reduced by measuring the flow directly with Promicon on the downcomer, right? And there's a short-term control on the fan, which is just done by the Promicon instrument. And then there is a long-term control, which is done by the O2 controller. So you have a cascaded controller, which in the long run keeps the O2 content in the kiln right, but at the same time avoids any large swings in fan control. This value very often is also used and fed into the plant expert optimizing system. Many plants have an optimizing system, either an expert system or a neural net, and they use this value in order to control the ID fan and even the burner and the kiln better. Again here, just an example of how much you can save. Huge savings, 120 euros per ton. So again, a very, very quick return on investment. Here, below 1 month. That's why this is our best-selling instrument in the cement industry. Downcomer is the big thing, big application. So again, here, bypass, another example. Not every plant wants bypass measurement, but the ones that do are really desperate. They have problems with chlorine or other things that they need to take out of the process, and they want to know how much gas they have to remove or they are currently removing with which result. And also here, it is for optimizing the process conditions and smoothing out the operation of the fan. So we want to extract the right gas amount, and with the right sulfur and alkali concentration. We want to maximize the waste heat of the clinker cooler, of course. It's a big energy loss, and the performance of the kiln. Yeah. So we have quite a few bypass applications. Here you can see a very nice example of a German organization, the VZD. Some of you might know them. It's a very famous organization of cement producers, and they have a scientific group that wanted to compare the measurement of Promicon with their extractive measurements. So they made a grid, and they found a very, very good match between our technology and their classical testing regime. Now, tertiary air, as I mentioned before, tertiary air is probably the harshest and the most difficult application, but a very important one. You have NOx formation in the main burner, you have NOx formation in your precalciner, and you try to avoid both. So what you have to do now is you have to have the right amount of total air coming from the clinker cooler. Main part of the air goes into the rotary kiln. Some of the air goes into the TAD. Now you want to reduce the total air on the burner so that you get a low NOx formation on your main burner. At the same time, you do not want to draw too much tertiary air into your precalciner so that you have a lot of NOx formation in that calciner. So for that, you need a measurement. You need to know how much goes out through your TAD. So you would like to have an optimal energy distribution, you would like to have a steady process, and you would like to reduce downtime of the calciner. The solution here is, of course, a good regulation of load on the precalciner and a very good tertiary air flow that follows that load, right? And we have seen clients that have reduced their downtimes of the calciner up to 60% by better controls. So for some plants, tertiary air measurement is a key element also to availability. And if I see Indian plants which have a high factor, load factor, high production factor, downtimes are certainly critical. So then, waste heat recovery. In the clinker cooler, you have several airflows going out. I've talked on the left-hand side now, the pyro string, the TAD. Of course, there's also the other side. You have the air going to the waste heat recovery section. And you would like to balance basically the output to both sides so that your neutral point in your clinker cooler stays at the same position. Now, this is very difficult because you don't always have the right clinker input. Let me show you this in an example. Here you have the clinker cooler, and on the clinker cooler, you have several inputs, and then you have several outputs. And it is important to be able to have the same balance of the output to the left and the right side so that the neutral point in the clinker cooler stays where it is and it doesn't move. Now, if you have different amounts of limestone falling into the clinker cooler, you have different air demands for the process of the rotary kiln. And that means that your air demand to the waste heat recovery is also changing. And for that, you need to have a good measurement to be able to control this flow. Otherwise, you will have the neutral point in your clinker cooler going back and forth all the time. Well, at the bottom line, it's again destabilizing the process, and you have more process noise than you want. So precisely to measure the heat gas going out of the boiler also allows you to have a better calculation of your efficiency. You would like to know, when you have a waste heat recovery boiler downstream the clinker cooler, how much enthalpy am I putting into my waste heat recovery boiler? You would like to measure the enthalpy flow. Now, I'm sure you have good temperature measurements on those pipes, but I bet you do not have any good flow measurement. So how can you calculate the enthalpy into your waste heat recovery boiler when you have no flow? You have to have flow. This is the key element. So this is what we're giving you. We're giving you an accurate and reliable flow measurement on your waste heat recovery boiler inlet. Here you can see a typical example. I mentioned to you at the beginning of my presentation that we would like to have straight runs, long straight runs. Now here you can see we don't have that. We only have a short run. In this case, we have 2 pairs of sensors installed instead of just 1 pair. And that is in order to better balance the stratification that we see in the duct. And as a result, again, we have a very reliable drift-free measurement of flow and combined with temperature of enthalpy into our waste heat recovery system. So, what are the motivations and benefits and commercial savings to sum up this presentation? Actually, usually the delta P measurement gives you blockage, it gives you permanent drift. And I'm usually telling this story in power stations because they have a lot of delta pressure measurements. In cement plants, there are not many delta pressure measurements. In cement plants, the dust load is so high that delta pressure measurements usually clog up in a very short time. And also other systems that use, for example, heat dispersion, like a hot wire anemometer, they drift. Ultrasonic systems, especially in hot gases, are usually not even they're even not capable of shining through the duct because the gas density is so low and the dirt amount is so high. Our system is the first one that gives a very good and traceable track record over hundreds of applications worldwide that we have done for a drift-free, calibration-free measurement with no zero drift, no span, absolutely linear. So this is the main advantage that we have, measuring gas flow in your plant. Probably the biggest key element that is still missing in order to optimize the process of cement making. So this is what I want to tell you today. In a minute, I will be happy to take some questions. I would, before I do that, I would like to give you a brief outlook on what Promicon is also doing at this time. What are we doing as a company? Are we just staying with airflow, or are we going further? And I have another very interesting instrument to announce to you. You can see here. This is a new way of measuring gas flow. We have introduced this system a while ago in the steel industry because the steel plants need to measure gas temperatures up to 2000 degrees Celsius. So measurement right out of the converter or out of an electric arc furnace. They want to know the gas flow as well, but at 2000 degrees Celsius. So how can you put a sensor into 2000 degrees Celsius? It will melt, right? So we developed this state-of-the-art infrared sensor that looks at the light in the process and that has two sensors and correlates the light. And by this light correlation, we can also measure the gas velocity up to 2000 degrees Celsius. And since we are looking into the infrared, we also have equipped the sensor with technology that allows us to measure not only gas flow, but also carbon monoxide, carbon dioxide, as well as NOx and gas temperature. In one of our next webinars, I will talk a little bit more about this new technology, which might also become very interesting for the cement industry. For example, kiln inlet or calciner in or outlet. So this is the preview on what we are planning in the future. Promicon will stay committed to the cement industry in challenging all the environmental and cost issues they have. And hopefully we will have more installations with your plants and more contact to this great industry, which is very, very important to mankind. Yeah? There will be no bridges and no houses and no roads without cement industry. Thank you very much for your attention and for your time. And now I will be very happy to take any questions from the audience.
Thank you, Dr. Konrad. So before we move to the questions, I would request Dr. Shyam Dighe to please deliver the presentation, and right after that, we'll be taking questions from all the attendees.
Okay, all right. So shall I exit my presentation now?
No, you can keep it on mute and you can turn your video off, and then we will turn it again the moment Dr. Dighe's presentation will be over.
Okay, good.
Dr. Dighe, requesting you to please start your screen.
Can you see it now?
Not yet. You have to click on share screen, then select that, and then click on share.
Yeah, I did that. Okay, I'll do that again.
You have to select entire screen icon,
yeah.
And then you have to click on share.
Okay, can you see that now?
Yes, yes, absolutely.
So I'll go into the presentation mode.
Absolutely fine. Please go ahead.
Okay. Um, are you seeing my picture on the side, or are you seeing the main screen?
We can see your presentation.
Okay, very good. I'll continue the presentation. Again, good afternoon, all the audience, members of the audience. It's a pleasure and honor to present this at this seminar. Although we are meeting virtually, I one day hope to meet you when I come out to India. Getting back to the presentation, uh, the topic sounds long and uh, cumbersome, but basically, I'm going to present what uh, gasification, plasma gasification, can do to the cement kiln in terms of being able to handle solid waste uh, directly into the kiln. Uh, the presentation will consist of this bullets. I'll give a short introduction on the company, then give a short introduction on the plasma technology. I'll again keep it short on plasma gasification, and then get into commercial projects that we have done in plasma gasification. Then the major thrust of the presentation will be in the um, application to cement plant, and I'll talk about a techno-economic analysis that we have done to one medium-sized cement kiln, and later on we'll be having questions and answers. Akshay, I'm coming through okay because I'm not getting the feedback. Hello, Akshay.
I think we can hear you all well.
Oh, okay. So you can see my presentation also, right? Okay, I'll continue then. The company is headquartered in Pittsburgh, USA. We manufacture gasification system which use plasma heaters, which were originally designed by Westinghouse, the big corporation. Uh, Back in 1999, I bought the division from Westinghouse, and we have continued applying the plasma arc heaters to the gasification system. They are applied both in the waste to energy plants, and also we are developing applications for desalination, both of seawater and oil and gas wastewater systems. The company has, in my opinion, sizable intellectual property portfolio. It not only consists of the patents that you see on the slide here, but also the know-how and trade secrets. That is very key in our industry, because the plasma technology sounds very high tech, used for space research, things like that. But we have applied this using our know-how and uh, trade secrets to industries like foundry industry, steel industry, hazardous waste destruction, etc. So the technology consists of a plasma system that uses an electricity as a driving force and heats up the gas into superheated gas, which can be as high as 5,000 degrees centigrade. This is not plasma gasification. This is what the plasma system does to a gas. But the plasma gasification system is a regular furnace. In this slide, you see what we call a foundry cupola. It's a regular furnace using standard refractories. And it has regular steel components, valve, and stuff like that. And the plasma torches that I mentioned before are applied in the bottom section here. As you can see in this bigger picture, this is, if you can see my arrow, let me make it into a laser pointer. If you can see this area, this is where the temperatures are in the 3000 to 5000 degrees centigrade, far removed from the refractory. And this is where the destruction, gasification take place on a medium, which might be coke, foundry coke, coal, anthracite coal. And this is the waste that is put inside this regular furnace for gasification. So I want to impress on you that although we are using a very high-tech device here to generate the plasma conditions and therefore generate very high temperatures, these temperatures are contained by proprietary nozzles in the center part of the reactor. So moving to the next slide, the gasification is normally done in I'm trying to get my pointer back. Okay, so the gasification is done in an oxygen-starved condition. I want to impress on the audience that plasma gasification is not incineration. The organic components of the feeds are converted into syngas. Very key for cement industry because you are using coal combustion, which goes through a syngas, but it's immediately combusted inside the kiln. But in plasma gasification, we have syngas that is generated, which removes the pollutants of the feed, the chlorines and the sulfur, etc. on the feed. The inorganic material of the feed is converted to inert slag, which is basically a feed to the cement kiln. And the most advantageous point here I want to impress, besides the syngas volume being very low than the combustion volume, since the volume is low in that reactor that I showed, there is no fly ash generation. The fly ash and bottom ash are converted to this slag before the constituents become fly ash to exit from the reactor. So the syngas exiting from the reactor is very clean in terms of particle loading. Now I'll talk briefly on the commercial projects. Again, I want to give you a flavor that this technology, although it appears very high-tech, is grounded in real projects. Here you see some of the projects that we have done. This is an application in steel plant where oxidic material like HBI with high degree of oxides are converted to iron. This is a plant in Alcan. It started back in 2005 no, I'm sorry, 1995, and it's still running, and it uses plasma devices to recover aluminum from aluminum dross. This is a plant in Japan doing 300 tons per day of MSW. This plant down here is for automotive industry, where machining chips were melted into gray iron for casting blocks. And this is the plant in India doing 75 tons per day of hazardous waste. It's operating as we speak. And I will try to elaborate a little bit on this plant. This plant was put together by SMSIL, the Sancheti SMS Infrastructure Group. It is in their Maharashtra Enviro Power Limited company. They have an environmental division, and the plant is at Ranjangaon in Maharashtra. As you see, the reactor here is the plasma reactor, at the bottom of which there are two plasma torches, and rest of the plant is the waste heat boiler and the bag house and things like that. They also operate a landfill nearby where they direct the inorganic waste, non-combustible waste, into the landfill, whereas the combustible and organic waste is fed into the plasma system, plasma gasifier. This is a very busy slide, but please let me take some time to explain that. It talks about the type of slag that is produced. The priority pollutants like lead, cadmium, arsenic, mercury, hexavalent chrome, selenium. The criteria is here for the slag to be less than 0.01 units, ppm levels, and the typical results are shown in the next column. What I want to impress on you is its order of magnitude less than what is required by the TCLIP, the TCLP procedures. In the plant in Japan where this measurement was done, they have a very stringent requirements on this slag, but they are able to meet it, and then the slag comes out as water after the water cooling slagger in 1 to 3 millimeter size, and it is then, for that particular plant, they make into interlocking blocks. The TCLIP on the interlocking blocks is shown here, which is order of magnitude less than the requirement. For the cement kiln, we propose that the water-cooled slag is a feed to the cement kiln, can be reused in the cement kiln. I want to show you on the next slide the stack emissions. Again, this is very busy. Please excuse me for that. What it shows is the priority pollutants here, the dust, HCl, NOx, SOx, CO, and dioxins. This measurement is from the plant that was doing municipal solid waste, and also a waste called auto shredder residue. It's a residue that comes when you shred the cars, automobiles, and the steel is then separated out by magnetically, whereas the dashboard, headliner, the plastic component comes out as dirty rag, and that is called auto shredder residue. It's mostly plastic, very difficult to combust in an incinerator because it's very fluffy, it flies off. And here they were doing close to 250 tons per day of auto shredder residue. The slide, as I said, on the leftmost column shows the priority pollutants, the regulations requirements here, and the plant was designed with this target. The measured values at 2 different times are shown here. Again, I want to just highlight the measured values. The regulation calls for 0.5 grams per normal meter cube. We were 3,000th of a gram per normal meter cube. The ppm level of HCl regulation called for 430. This was only 39 and 22. Dioxins, which is very key element in plastic combustion, that was the key point that we were designing for. The regulation allows 5 nanogram per normal meter cube. We designed the plant for 0.05 nanograms, and here you can see the measured values, orders of magnitude lower. Again, my point that I want to make is the syngas can be combusted in the kiln, in the boiler, in the whatever processes downstream of the plasma gasification. The precursors of this priority pollutants are so low that the kiln can meet the regulation without having to do any modification of their existing APC, air pollution control equipment. That's the key point I want to make here. And this is from measured data on actual plants. Now, let me get into the crux of the presentation, the applications to the cement plant. The plasma gasification plant has the capability of accepting different inputs, different feeds. And here, what I'm trying to impress on is it could be solid feed, liquid feed. Mostly, we would like to use the organic content of that feed. So the waste normally would come from pharma industry, dairy, agricultural industry, chemical industry, pharmaceutical industry, refinery, etc. So the type of waste, because of the nature of the plasma gasification, very low superficial velocities, intense temperatures and the critical zones of the destruction, gives you a wide range of solid and liquid material feed. This is a very key point to a plant operator, because when the waste is coming into the plant by a truck, you don't want to send the truck back just because it doesn't meet certain critical feed criteria. And that is very important when you are operating 24/7 operation with the customer. Sorry. The output of the plant could be electricity if you use a steam or combustion cycle or combined cycle downstream. It could be plain fuel gas, the syngas that I mentioned, that can be fed to the kiln. And the vitrified slag is another output that can be fed to the cement kiln. The electricity and fuel gas are usually either or options, and I will discuss this later in my presentation. But if you need electricity, the capex increases because you're putting a combined cycle or steam turbine plant following the gasification plant. If you use fuel gas, capex is at times half, because all those turbines and waste heat boilers are not required. Steam generation boilers are not required. We can just feed the fuel gas directly into the kiln. Now, for this particular techno-economic analysis, the boundary limits we have used is this. The plant is situated across the fence from the cement plant, and the waste is brought into the plasma gasification plant, which takes a little bit of power to start the plasma gasification, produces fuel gas, comes across the fence to the cement plant, as well as the slag that is produced comes across. So for this particular analysis that I'm going to present, and it's a very simple analysis I want to present today. All the details can be discussed at much later time, but please remember, these are the boundary limits. Fuel gas into your cement kiln and slag into the cement kiln. Again, please excuse me for this busy slide, but I'm just stating the assumptions of that particular layout that I mentioned for this techno-economic analysis. The plant capacity considered was 30 tons per day of the hazardous waste, operating 330 days per year. The capital investment for the gasification plant was 20 rupees in crores, 20 crore rupees. The power consumption of the plasma gasification plant was only 150 kilowatt hour per ton, and the power rate used was 6 mils or 6 rupees per kilowatt hour. The calorific waste was 4,000 kilocals per kilogram, and there is a disposal service fee that the waste generator pays to the plant when it destroys his waste, and that was the assumption, 15,000 rupees a ton of hazardous waste. The fuel gas for this study was generated at 1200 degrees centigrade, and the amount of fuel gas fed to the kiln is 4.6 million kilocalories per hour. Converting it into megawatts that cement kiln is familiar with, from 30 tons per day capacity plant, 4.6 million kilocalories per hour equates to 5.4 megawatt. 5.4 megawatt of enthalpy is available into your kiln. These are the enthalpy of the fuel gas. We assume manpower for the plasma gasification plant at this parameters. So I just wanted to present these numbers because those are the assumption numbers for the techno-economic analysis. The operating cost that follows is here. Let me give you the bottom line. The annual operating cost is 6.5 crore rupees. And as you see here, the biggest component, if you notice, are not the power cost, labor cost, or miscellaneous cost, but it's the depreciation cost, interest costs, which are almost half of the controllable cost that you have, power cost. The depreciation, I have not given you that figure, but we assume 10% depreciation, and the depreciation rate was 10%, and the interest rate was 8% for the Indian conditions. The maintenance cost was taken as a percentage of capital at 5%. Now, here's the bottom line on this techno-economic analysis. For a total operating cost of 6.5 crores per year, the disposal fee is, of course, the biggest component. The fuel gas saving is in here. but the assumption is very stringent, in the sense we have assumed the value of fuel gas at the value of natural gas price in US. I didn't have the numbers for Indian conditions, but this equates to $3 a million BTUs, or $3 a thousand standard cubic feet. So in terms of Indian rupees, which you may be very familiar with, if you, it is valued at let me just see, about 8 rupees a meter cube. And I'm sure it is more than that, but right now I'm just going to go with this figure. So there's an annual saving of about 18 crore rupees per year. For a net profit, 18 minus 6.5 is about 11.4 crores a year. And for a 20 crore investment, it's less than 2 years payback. The biggest element which I have not quantified here is the emission control saving. It is very specific to your plant. The plant operator knows that when he puts hazardous chemicals directly into the kiln, what capex and what opex is involved in making sure you meet your local state pollution board standards. I did not want to hazard a guess here, because it's specific to a specific location, specific state, specific size of the cement plant. So when we revisit this for individual case studies with you, hopefully we'll get some inquiries from individual cement plants. But you will find this saving is a sizable saving and will further decrease the payback period. We also did the sensitivity analysis on this plant. The likely scenario I presented was this. The best scenario where we increase the Indian content and reduce the capex, the disposal rates are higher, the calorific value is higher. It could be less than a year, but it could be as much as more than 3 years if the capex goes up and the disposal fee drops down and the waste that we are getting is not energetic enough. So that could be slightly more than 3 years. But the likely scenario is within 2 years, you can recoup your capex. So the ROI is very good on this plant. Having said that, I will end my presentation. I'll leave this slide here. I've provided the contact number, digasv at aquasourcetechnologies.com. And you can visit the website, which has lots of technical information, brochures, and things like that. So having said that, thank you very much for listening, and I'll end my presentation.
Thank you, Dr. Dige, for sharing your presentation and sharing a wonderful aspect. I would request Dr. Conrads to please turn on his video and audio. Dr. Conrads, we will initially take your questions and then we will take Dr. Dige's question. There's a question from country head of Mazda Limited is asking, is the alignment critical between both the sensors for Dr. Conrads?
Well, good question. First of all, the sensors have a distance, right? So that distance needs to be kept. If you have a different distance, then you need to correct that in the parameters. So the distance of the sensors is has a linear influence on the velocity that you measure. Now, That's one thing. The other thing, alignment. If the sensors are not exactly in line with the flow, but slightly angled, that influence is very small up to a certain angle. So within plus minus 2, 3 degrees, there's nearly no difference in measurement that you see. And the third question, of course, is how parallel are the sensors? Are they parallel or are they twisted? And of course, they have to be parallel, and that's why we deliver our adapter pieces with a spacer bar that keeps these adapters really parallel. So when you weld them on as a pair, and then all the sensors automatically are parallel. So it is critical, and parallel and distance both is a thing that you have to look at and make sure it's correct.
I hope that answers Neeraj your question. Neeraj is with us. Neeraj, does that answer your question?
Yes, it has answered.
Thank you, Neeraj, for joining. Moving on, we have a question from Dalmia Cement Bharat asking, are you manufacturing steam flow meter?
The answer is no, we do not. So we have no steam flow meter in our portfolio. Sorry.
Wonderful. Another question from Dalmia Cement again. Is there any instrument to measure compressed airflow?
Okay, that's a premature question. We are looking at that. There are several requests from the industry to be able to measure at very large turndown ratios. And one comes from the petrochemical industry, which we're looking at, and the other one comes from, indeed, the manufacturers of compressed air, of compressors. Turndown ratio is a very big issue, and we are looking at this. We do not have a system on the market yet, but it's something that we're looking at.
We have a follow-up question from Neeraj asking that he just went through the presentation and he saw that the dust loading has no impact on performance. Are there any other parameters that can affect the performance of the meter?
Well, this is a very, very important question. It's a digital flow meter, right? So what we are doing is we are measuring the time signature of these particles flowing by. And now let's just assume that you have a very dirty antenna. There's a lot of dust on the antenna. In this case, the amplitude of our signal might go down. But if the amplitude goes down, this does not affect our measurement, because our measurement only looks at the time shift between the two signals. And this is the point. As long as we still see a sufficient signal, the digital calculation of the time of flight will give us exactly the same reading. I often compare this to a CD versus a long play record, an analog long play record. If you have a long play record and you have a scratch on the record, you can hear every scratch. If you have a digital CD and you have a small scratch, you can't hear it because it's corrected. The digital algorithm is tolerant enough to still give you the original music. Only if you exceed a certain threshold, you get problems. So the answer is performance. If you see a reading, it will be accurate. If you cut the cable or you completely cover everything so bad that there is no signal received or no sufficient, then the reading will go from accurate to error. So there's no in between between accurate reading and error. Hope that answers the question.
I hope absolutely that answers the question. I'll move to Dr. Digge with the question that we have received from Tyson Group. What is the capex for 300 TPD MSW plant?
300 TPD capex. Again, I'll give a ballpark figure. The 300 tons per day. We would at the one at in Japan was somewhere around $50 million. No, not 50. $20 million. The plasma gasification system.
I hope, Mr. Nouri, that answers your question. Moving to the next question for Dr. Dege from Talib Hussain, head from YCAT Group. He has written, Sir, can you let me know the specific steam generation with MSW having 23% moisture and CV between 1500 to 200 kilocalorie?
Okay, I don't have that handy right now. If you could please send me that question, I will answer that.
Absolutely. We will share that question with you, and I would request Mr. Talib to please reach out to Dr. Dige with your questions and further queries. He'll be more than happy to connect with you and resolve your challenges. Moving on, we will see if we have any more questions that we cannot see right now. But if any of the delegates have any question, please raise hand or write your question on chat, and we will take it to our speaker. We have one more question. Okay, there's a statement from Nori. It says it depends on the quantity of syngas generated. Okay, that's another thing. So we cannot see any questions. On that note, we would like to conclude the day one with two amazing speakers who joined us from US and Germany. Thank you so much, Dr. Dege, and thank you so much, Dr. Conrads, for joining us. It was a pleasure to have your presence for the day one of the WHR World Conference, and we look forward for your further participation in the future conferences as well. Thank you so much for guiding us. And
thank you
very much.
Moving on, we are here with the day one of the conference, CEM WHR 2021 Virtual Edition. This is the second annual we are doing. And before we conclude, I would like to thank our associate sponsor, Aquasource Technologies Corporation, Promicon, and Setsan India. On that note, we look forward for your presence tomorrow at the same time, the time we started today. Which is 10 in the morning, but registration link will be open by 9:30 so that you can join us and take full advantage of the networking table or the virtual table that we call, and you can connect with the leaders and the pioneers here, the subject pioneers. Tomorrow, we are looking forward to have some wonderful technical presentations and panel discussions and award ceremony. Till then, we look forward to connect with you. Stay safe, and we'll join again tomorrow morning. Thank you so much.